so we're back on recording. So to start off with the relevance, the first thing I'm going to do is be completely annoying. And this is some basic geometry. Okay, some basic geometry. And you've already kind of experienced these things. So what's this one? What is that one? You can tell me what that basic geometric shape is. And of course, you know, you're allowed to use technology, aren't you? So if you're not sure, what you do is you open up a new browser window, and because I use it a bit, it's already there, and you put into Mathematica, and hopefully that'll give me what I want. Sometimes you've got to put brackets up there if the thing, yeah, there you go. So that's it. Okay. Now what have I done wrong? Anybody pointed out? It's so easy to do mistakes. So this is why I want, I'm happy to do things here because you guys, you're important. And of course what's going to happen is, this is the kind of thing that's going to get you unstuck. Okay, so let's go back to what's the error here. The basic idea is, what's the problem? Okay, so put it in the form of an implicit equation. And this is the trouble that you get with maths. You can be thrown around so much like a washing machine. And I'm just doing this a bit it's a bit naughty of me to do it this way. But what I'm trying to do is to get you to recognize that when something doesn't present well, it's not the end of the world. Okay, you just got to say, okay, what is it that the idea is about? So let's go back to the idea. Okay, the idea is what? Let's go back to the basic idea. So we'll come back to this one and we'll take the y out, and we'll take the square root out. In fact, let's not even bother with that. Let's just get rid of all of that, because this is an encyclopedic thing. Okay, it's an encyclopedic thing. So you can put in to Wolfram Alpha these kinds of things, and they'll help you develop this. So the Cartesian equation for a circle. Okay, so how is it that we came about in such a roundabout way? And I do that deliberately sometimes because it's important for you to recognize that we're dealing with functions like this all the time. You've had 13 years of training of why something, okay? And then when the form changes, it's all like, what the? So how do we go from this, okay? How do we go from this to this? And how are they even related? And guess what you're in the middle of? You're in the middle of vectors, and you're supposed to know the answer to that question. How are they even related? How can you pull out the skills that you've got with your, you know, algebra, quadratic equations, and reconcile this? Okay, how do you do that? So this one here is often called the radius, or r squared. So you can always check. So this morning I want to make that link. Okay, I want to bounce around that link and say, well, how do we reconcile that? Because you're going to be expected to do it in the stuff that you've got there. All right. So what this is, as we saw from Mathematica, is a circle with a radius, and the radius is r. So I'm going to say r squared, either or. Okay, you can call it either or. Okay, I could have put a comma. Either one is okay. And so when you look at the form of the equation, for example, you'll have a x squared plus y squared, and this is often done, is equal to 9. Well, how's that even match that? What's changed? It's just like what I did before. What's changed? Well, where's a or r? They're there. They're just in that form. And you're expected as a student to pick that up. on some basic level. Alright, so let's move this thing around a little bit. If I move the circle around to the side, and I'll just make it simple, that's fine. What do you think the equation is there? And let's do the radius. Well, the radius is going to be 2, isn't it? So what's the equation? Well, y squared is going to go along without any problem. And we've already said 2, so the radius 2 squared would be 4, so we can have a 4. I've got to do something about my stylus, it loses its way. But what's happened to x? X has been moved in the positive axis, and when we did perfect squares, when that happens, you put a minus. So the form of the equation has just been modified a little bit. Okay? And likewise, if we move the equation up, what would be the difference there? The difference would be x hasn't changed because it's still on the y-axis. What's the radius this time? The radius spans that gap. That's 2. So 2 squared is 4. And then what have we done with the y? It's gone positive. So inside the bracket, that's y. We've got to shift it up to 3. Okay? So what you can do is use your technology to check any of these. So and that's what I encourage you to do. Okay? So what did we say? X squared, somebody just remind me, plus bracket y minus 3 bracket squared equals 4. Was that right? Let's see what that does. See, it moved it up. Centered it on 3, came down to 1. So we're at least as good as Mathematica. Okay? We can tick ourselves. So what happens then when we get a quadratic that kind of doesn't make a lot of sense? So let's try and do this. Because I know this is coming up for you. This is immediate now. Okay, let's do this. Alright, when you look at that, what does that even mean? You're doing vectors, you get a question, and that's on the sheet. What's going on? So what skills do we need to recognise to unpack this? Any suggestions? What's one of the skills that you might need to do?
Undo.
Undo? Yeah, we can do undo. I'd really like it in this form. This is the perfect square form, isn't it? Because the perfect square form will land me somewhere around. You know, this is the link now between our general form and this is what we got. Alright, we got this one, didn't we? Look at this, it's rubbish. What do we do with it? So what we're going to do here is we're going to complete the square. So you take for those of you that watched it, you take the coefficient and you halve it. And then you take that and you square it. And that's the square number that goes together with these two to give you a perfect square. And that is a perfect square in the form of, who can tell me what goes here? X times x is x squared, tick. X times this thing times 2 is 2x, tick. So this thing's got to be 1. And 1 times itself is this one, tick. So we've now what did we do? We just went, you can't willy-nilly add 1. So what have you got to do to balance the equation? Subtract 1. So I'm going the long way, right? I'm being annoying with my long way. Okay? So now we've got one part of the geometry equation. What about this one here? So you take the b term, you halve it, you take the that result and you square it. That's the square number that goes together with those two terms to give you a perfect square. And what is the perfect square? It's going to be 2, isn't it? So we already had x plus 1 over here. And you can't just add 4, come on. So what have you got to do? You've got to subtract the 1, don't forget that one. And we're going to now subtract the 4. And so now we've got something that looks like what we're looking at. Okay? So I don't know if that's going to come out to a nice number, but we'll find that out in a second. So what our flotsam and jetsam of unchanged algebra is, using quadratic formula techniques like completing the square. So if I plus 4 and plus 1, I'll get plus 4 and plus 1, that's undo. And so 7 and 4 is 11 and 1 is 12. Okay, so that is going to be expressed in terms of a radius, isn't it? That's going to represent a radius. So that's our radius. Okay, so what have we got here? Now, I didn't do that before. I left it off deliberately. I did 1. What happens when you get 2 terms? Now, the general forms of these things are usually x minus h and y minus k or something like that. That's how the textbook's presented in school. And so sometimes it's a bit hard to recognise the concept, and hopefully I'm moving you through the concept reasonably well. So we've got x at plus 1, which means it's going to be at minus 1. We've got y at plus 2, which is going to be at minus 2. And so that's the centre of the circle. And what's the radius going to be? It'd be easy if it was 9. So this is one way you try things out. You're not sure. Okay, so if it's 9, it's 3 squared. You know, if it's 16, it's 4 squared. That's somewhere in the middle. So it'd be nice to have something squared, wouldn't it? Something squared if it was 12. So probably just the easiest way to do it is to say it's the square root of 12 squared. That's the radius. Okay? And so that'll give us the number that we're looking for. Alright, so what this means then is that we've got this circle. Oops, not very drawn very well, but we've got the circle. Now, how do you check that? Use your x1 equals 12. Let's see what Mathematica does with it. X plus 1 plus 1, and what was the other one? Y plus 2, was it? 3. Oops, what am I doing there? Y plus 2. And what do we say? 12. Let's see what that looks like. Okay, so we're spot on. Okay, we've moved it to the correct location, 1, and down to minus 2, and then we've got our radius. Okay, so it's not terribly difficult for you guys to start to walk towards technology as a help in the development of your parts. Okay, so what do we do then? You've been learning about 3D, so we're going to do a little bit of 3D, and I'll do an example of that one as well. So one of the things I want to encourage you to do is a bit of sketching, because I know that this is your stable, okay, and Mary's already introduced 3D, so I'm happy to do this. So how do I change? Some of you might know what to do implicitly already. You might be just intuitively winning, and that's good. But what I want to do is just show you a couple of things. So if we just push that over, push him over, be a bully, push. So what we'll get is y sitting there with x. Okay, it's been pushed over. Can you see that? And then what we want to do is rotate that around. And so in rotating y around, we'll get y and x sitting like this. Okay? And then all you do is add your vertical, and you'll find that you've got your z. So I would encourage you to do what I just did there until you got it right. Okay. Now the way that you sketch things in 3D, how do you do that? How do I sketch things in 3D? You use parallel lines. It might not have been obvious from the sketching in the lecture, but that's what you do. So this is positive out here, negative at the back. Positive out this way, negative at the back. Positive up the top, negative down. Okay, so in order to do a coordinate, where we get a coordinate and we might get some point Q, I'm just being completely random, and so what we have is 2 and 4 and let's call it 7, and you're expected to interpret that in a 3D sense. So what are you going to do? Well, you're going to draw your X and Y, then you're going to draw this one off like it's Y equals X, but a bit longer. Okay, this one here is X, Y, Z, and so X is going to be at 2, so we're going to come 1. We don't want to go too far because Z's at 7. Actually, I might change that. I might just make that maybe 3. Okay, so X is 2, so we come across here and we write a 2. Y is 4, so we come across here twice as far, that's 4. And then Z is 3, so we're going to go up 1, that's 2, that's about the same length, 3 is about there. Now, it hasn't helped, has it? It's just like, what? Are you kidding me? So I really encourage you to do the following bits. So now we're going to use our parallel lines. Okay? You just do this sketching. So what we're going to do is we're going to start at the X1 and we're just going to draw it across, keeping parallel to the Y-axis. Parallel to the Y-axis. So we're just going to draw a nice parallel line like that. Dotted. Then we're going to go to 4, and this time we're going to draw a parallel line to the X-axis. So it's going to go like this. We can see where they intersect now. That's going to form an edge. Now it'd be nice to do the rest of the box. So we're going to go up, parallel line to Z, and that's on the back of the box. So that's going to be a parallel line to Y. And then this one here will have to be a little bit cheeky because we're going to be parallel to Y. It's going to be parallel to this one. So whatever we do here has to be a parallel line to the Z, to the X-axis. Okay, this one now is going to be parallel to Z, and so what we've got is an end. Okay, this is not straightforward, folks. If you're feeling a bit intimidated by this, in a way it's good, but you've got to do it. I want you to practice this. Do your own. Make up 6 of them. Okay, now this one here, parallel lines, up we go. Okay, this one here is going to be parallel lines, so it's got to be parallel to the X-axis. So let's see if I get that right. Nearly. It's pretty close, I reckon. Oh, that's going to be out that corner, isn't it? So up a bit further. And then we'll go across. Whoops. Fudging a bit of fudging. But basically what you can see is what Mary did. Okay. There you've got your bread box. Okay, where's the coordinate of interest? 2, 4, 3. The coordinate of interest is that one. Okay, so we can erase some of the superfluous bits that aren't going to be helpful. And I think she did this, so probably not really that important for me to do it. But this point, and if we have a vector, if we were to put this in vector form, and what form is that? That is the form of, what form is that? That's component form. So that's the one that I prefer. Okay, there's another form. What's the other form? They're the same thing. Now you'll have to pick your preference as a student, which one you want to work in, and you can change them fairly readily. Okay, some lecturers love this form only, the unit form, okay, because it's based on the idea that when you're sitting in your thing here and you've got 1 and 1 and 1, that's your I, J, K, and often not put a little thing on top of it. I probably should do that. And I should call that K, shouldn't I, really? K. Alright. So I wanted it to be IJK, so X, Y, Z. So there is a little bit of a crossover there. There's that translation between forms, and that's something you guys are still getting used to. There is a lot to do. There is a lot to do. So this one here, if I'm not mistaken, will be up here. And not done on graph paper, not beautifully neat. It's intuitive. The idea's there. Okay. Now the question that we had before was, okay, you can put these arrows in, but what else can you put in? What other things? We were doing some basic geometry. Well, we've done really basic geometry there. We've done a bit of a 3D shape, but we had these circular shapes. I wonder what that looks like. So let's have a look at that. Let's go back to blue. Alright, so we're looking for let's see. What does that mean? It's just some algebra. I can see that it's got some quadratic information in it. That's nice to know. But what else does it mean? Well, this is where, as a student, you're supposed to take your previous knowledge and recognise that this is going to be the plot of a shape in 3D. Okay, that's not so easy, is it? It's not so easy to do. But in effect, this is what we're going through. Okay. All right. So I'll keep going. Who can tell me what the first step might be?
Complete the square.
Yeah, so just complete the squares. So if you go ahead and complete the squares, I haven't taken this from a question, so my radii are going to be wrong, but I'm not really bothered by that. At the moment, we're just doing the skill, aren't we? You take that and square it. That's the square number we're after. So x squared minus 2x plus 1. Now we can't just willy-nilly add 1, so we'll have to subtract 1. And that's a perfect square of the form. Okay, minus 1. This one here, we take this one and we halve it. And we square it, so this is going to be an odd one. There's your indices laws at work. That's the square number that's going to go with. And give us a perfect square. And what's the number going to be? I'll give you a clue. It's that one. And it's a positive. Y squared, tick. Y times 3 on 2 times 2. The 2's will cancel, and you're left with 3y. 3 squared, great, tick. Okay. Now you can't just willy-nilly add 9 and 4, so we've got to subtract 9 and 4, and look at what's happening. Fractions are coming in. good old fractions. So we take the coefficient and we halve it, and we square it, that's the square number that goes together with our z squared minus 2z plus 1 gives us a perfect square in z of -1, z squared tick, z times 1 is z times minus 1 is minus z times 2 is minus 2z tick, minus 1 times minus 1 is plus 1 tick. Okay, now we had to add 1, just can't just willy-nilly add 1. Okay, so we've got to subtract 1, so we'll put that there, and we've got 16. Alright, so now it's looking like we've got a 3D circular thing happening. We've got undo, undo, undo. So we've got y plus 1.5 z minus 1 equals all of this, 16, 17, 18, 18 plus 9 on 4. So in order to get that to work, being the annoying long way teacher, we've got to get 18 on 4. So that's a 1, isn't it? So what do we have to multiply that by? 4. What you do to the bottom, you do to the top. So 4 18s, 4 8s are 32, 4 1s are 4, 5, 6, 7, 72. 72 plus 8 would be 80, so it's 81 on 4. Well, that's handy. I missed a step there. I shouldn't do that. Not at this early stage, you're not ready yet. Some of you are going, I can do it, Jason. I know, but we're here for everybody, not just you. And so, correct me if I'm wrong, but that's 81. Now that's got a square root thing happening to it, isn't it? So that's handy. So what we've got is x minus 1 plus pi 3 on 2. Now did you all pick this up? Is this relevant? Okay, and 81 on 4 is 9 on 2 squared. So 9 on, the reason I'm doing that is because that's the radius. It's not correct to say that that's the radius. 81 on 4 is not the radius. Remember, that's your square. Okay, so what do we got? Let's have a look. Let's see if we can draw this thing out. So we've got our 3D. We've got x is at minus 1. So that's come forward to 1. That's the rule. Y is at plus 1.5. So that means y is minus 1.5. So that's about there. Z is minus 1, so that means it's plus 1. And so our radius is 1.5. So who wants to do technology and tell me what to do? Put this in to technology and tell me what to do. In the meantime, I'll do some parallel lines. That's about right. On 2, 2, 4, 6, 2, 4, 2, 4 is 8. It's like 4.5, so it's quite a big. How'd I go? Quite One big swoop. What's this thing called? What's this thing called? Did you put it in technology, anyone? What did it give you?
I'm just entering it now.
Good job. So we've moved from the equation of a circle, moving the circle around, and then when we do this algebraic manipulation, which there's a fair bit of it, to get this thing, what's this thing called? Any thoughts? A sphere. Well done. Brilliant. Okay, so what we can do is put our version together. So I might just move that over a little bit so I can just line that up. It doesn't need to be that big, does it? There we go. So we've got x minus 1, because the rule is we go positive, y plus 3 on 2. Hopefully that'll cope with that. Z minus 1, and our radius was 9 on 2. So we thought. And so if we look carefully, we can see that, and there's all our work, alternate forms, very good. So we can see the movement of the plus and the minus. So there's our 0. Mathematica doesn't do it very well, but you can also do this in Python, but we're not going to do that at this point. That's something for later. Alright, so basically what happens is we get a variation of a theme. Now what can happen with our algebraic equations is that we can get our bits and pieces and we can modify them a little bit. And by that what I mean is, let's say we just had this bit, and then the question went on to say that Z was infinite. So this is a modification of the concept. So we've gone from basic geometry, basic algebra that matches the geometry, shifting it around, to shifting it around in 3 ways. Then we're saying, well, what happens if we take that 2D form and make a comment about Z being infinite? What does that look like in that form? So I'll do it here with this one because this is y and x. Remember what we've done here is we've pushed y and x over. So when we draw this infinite Z, let's call it infinite Z. So this is now conceptual, right? So what we're going to do is push y over and rotate it. So what we've got is our x, and this is where it gets a bit tricky, isn't it, conceptually? Y and Z. Conceptually, if you've never met any of this stuff before, it can be quite harrowing. What I've got to do is draw this one at -2 for y, which is down the back here, and -1 for x, which is down here, and just find where they meet using parallel lines. And that center is that one there. But look what I'm doing now, and this is conceptual now. This is your math journey where you're joining 2D Cartesian to 3D. And what's happened here is that this circle now needs to be reproduced at the radius of whatever we said it was. Okay, and the way that I would have to do that now is this kind of circle thing that goes around. I've got to do it justice, so I may have to have another go at it, but essentially I'm going to draw like a football thingy to try and get the sense of circularity. So that's 2 vertical. So let me have another go at it. Does that look like a flat circle looking down from above? Yeah, that's not too bad. So if it's got an infinite z, what does it mean? An infinite z means that the edges of the circle are going off to infinity in all directions, positive z, and all directions, negative z. So what we end up with is effectively, what's this thing? What's this thing? It's not toilet roll. Yeah, it's a cylinder. Dun, 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 dun. So what we've been able to do is take our algebra, our quadratic formulas, and bring a new kind of understanding to what it means. So hopefully what this is doing is filling in some blanks for you. Okay, the simple stuff that you're doing with vectors and addition and subtraction, and we'll do that next. So I'm going to pause now. I'm going to press pause. It's only 12 o'clock, so we can do the next bit. Now this is where it comes to your requests. You must have some nagging questions about vectors, dot products and the like. So let's just pause the video and we'll come back and we'll have a look at that for the next half.